We've seen how we can find a definite integral. So we know how to integrate a function, a polynomial, and we know how we can start to substitute some numbers in, so we get what we call a definite integral and get some values from it. What we want to do is move that along now to use it for its first major application, and really its biggest application, and that's to find areas by using integration. And what we want to do is use a simple example to start off with to show that the integration of a function actually leads to the area, and confirm that with its actual formula. So if we investigate the first one here, and that's the area bounded by a straight line, y is equal to 2x. The lines x equals 0 and x equals 1. So if we draw that up, and it's really important to draw it up so you can see it every time, and we'll show you more examples later on exactly why it gets important to draw it up. So if we draw that, we see the straight line 2x, we see the line x is equal to 1, and x is equal to 0 is in pink. That's actually the y-axis. So the area we want to find is this shaded region here. So as you can see, that's a nice little triangle. So again, let's have a look. The area of that triangle, if we looked at it, would be half times the base, and the base is 1 unit, and the height is 2 units. Now, the area there is 1 unit squared. So let's have a look at what we can do when we actually integrate it. So when we integrate a function, we actually get the area below the function to the x-axis. So if we're integrating 2x here, excuse me, integrating 2x here, it's actually going to give us the area underneath that curve to the x-axis, and the limits of integration is going to tell us, well, how far across we will be integrating. So we're integrating from a point, this is a point here to a point here, so it's going to give us that area here. So if we integrate 2x, we get x squared. We're going to substitute 0 and 1 in. So, and we treat like our definite integrals that we did before. So 1 squared minus 0 gives us 1. There we go. We can see that it's exactly the same area as we got when we actually apply the formula for a triangle. So there's a simple little showing that it's not a proof as such, but we can show that the area here is what we're going to get when we integrate that function between the two limits there, because it works out the same as the area. Now, if we had a triangle every time, well, we can use the formula, but we're not going to get a triangle every time, obviously. This one you could use the formula again in question 1 because that's going to give you a trapezium. So we go in between 1 and 3, and also we've got the straight line. So the area under the curve to the x-axis should be given to us by 1 to 3 of 2x plus 1 dx. We integrate 2x, so we get the 2x squared on 2, and the 2's cancel. 1 becomes x, and we go from 1 to 3. So we substitute 3 in, we substitute 1 in, and we get 10 units squared. So there's our area of that. Now if you want to confirm it, you can stop the video and apply the area formula for a trapezium, and you can see that you should get 10 units squared. In question 2 here, this is one where we can't start to use a nice formula because we've got a curve. Y is equal to x squared. So the area between x squared, the x-axis, and 0 to 1 there, it should be given to us by this function. So integral between 0 and 1 of x squared dx. Again, the integration, usually the integration is reasonably easy. So we integrate and get x cubed on 3, 0 to 1, 1 cubed on 3, minus 0. And it's nice having the 0 in there because it generally works out to be 0. Going to give us 1/3 of a unit squared. So that's the area inside there. So we're looking back to our definite integrals, so and keeping them in mind when we want to start finding the area under a curve.